Let's do another example of a probability distribution. What I'm going to do here is I'm going to use a frequency distribution here. So let's say a sample of households are surveyed. And let's say they're asked how many TVs they have, and then they take the data that they get and they organize it into a frequency distribution. And let's say the possible values are 0, 1, 2, 3, 4, 5, 6. And the frequencies are 1, 8, 12, 5, 3, 0, and 1. So this is a frequency distribution giving us the data for this particular data set. And what I'm going to do is I'm going to randomly select a household. And we're going to let X equal number of TVs for selected household. Okay, in this case, X would be a random variable because I can't predict with any certainty how many TVs they're going to have. And I can construct a probability distribution in this case. So the possible values would be either no TV, 1 TV, 2, 3, 4, 5, and 6. So what about the probabilities? Okay, well, what we learned before is if you have a frequency distribution, to find the total number of outcomes, we need to know how many households there were, right? And so we can add these up, add up the frequencies, and we get that there were 30 households. One of those 30 households had no TV. So the probability of getting no TV would be 1 out of 30. 8 households had 1 TV. So for 1, the probability is 8 out of 30. And then 12 out of 30. 5 out of 30. 3 out of 30. This would be 0 out of 30. And 1 out of 30. So, and I always, even if I could reduce these, like these, most of these are going to reduce down, I keep them the same denominator because then I can go and I can add all these up because you need a common denominator to add them up. And so you just add up the numerators, and when you do that, you're going to get 30 out of 30, which is equal to 1. And that'll always happen because these top numbers are just the frequencies here that you added together to get 30, right? So you're always going to get the probabilities to add up to 1. So pretty much any frequency distribution can be set up as a probability distribution. You can think of it any data set, like any population. If you organize the data in the population using a frequency distribution, then you could make a probability distribution out of that. And then it's like you're randomly selecting an observation from the population, right? Which is what you do when you sample. And so these probability distributions are going to play an important role when analyzing the sample and the rules of probability that determine how much error you're going to expect to see. So the idea of distributions here is really important, and it is connected to the idea of frequency distributions from earlier when we organized the data set. So we could also do some pictures here. So maybe I'm going to do the picture under here because I want to show you one more thing over here. So 0, 1, 2, 3, 4, 5, 6. Okay, and then looks like these go up to 12. So maybe I'll do 2, 4, 6, 8, 10, 12. So 2 out of 30, 4 out of 30, 6 out of 30, 8 out of 30, 10 out of 30, and 12 out of 30. So 0 is going to go up to 1, which would be about right there. 1 is going to go up to 8, which is right there. 2 is going to go up to 12, which is right there. 3 will go up to 5, maybe about right there. 4 is going to go up to 3. 5, there's just not going to be anything there. And then 6 will go up to 1. And so here you got a picture of your distribution. And it is not unlike the histogram, except you have just straight lines. So for the probability distributions, you just draw the line up to where the probability is. So it's just like a histogram, right? And in fact, you could show that this is actually a right skewed distribution. So probability distributions can have shapes just like frequency distributions, and it very much looks like the histogram. It's just, in this case, you're looking at the probabilities. So another neat thing you can do is with this notation, since the variable is x, I can do probability problems very concisely. I could say like the probability that x is equal to 2. And so this would just be the 12 out of 30, right? 12 out of 30. And then you could find, I'm not going to worry about getting the decimal here. Probability that x is equal to 5. Looks like that's 0 out of 30, so that's just 0, right? I could do probability that x is greater than or equal to 3. So that would be adding these 3 up. So that would be like 9 out of 30. Those are the 3 that are greater than or equal to 3. Or I could do the probability that x is strictly less than 3. And if I do that, then strictly less would be 0, 1, and 2. So that'd be like 21 over 30. And so there's all kinds of possibilities. Also notice, if I wanted to find like the probability, of at least one TV, you could think of this as like 1 minus the probability of no TVs, right? Because at least 1 would be all of these, and the probability of the only probability you're not including is the probability of no TVs, right? It would be that one family here. So you could use the complement rule, 1 minus 1 over 30. You can also think of it as this. All of the probabilities add up to 1, right? And so instead of adding all these up, I can just take 1 minus this one right here, which is 29 over 30. Okay? So there's all kinds of things that you can do here. And so these frequency distributions forms a really nice context in which to do to study these probability distributions, as well as this really neat, concise notation.